So the next topic of today's lecture is all about UJ format instructions. Specifically, we're going to talk about the different jump instructions in RISC 5. So for branches, we actually assume that we won't want to branch too far, so we just specify a change to a PC, so it's relative. For general jumps like JAL, which is jump and link, we might want to jump anywhere in code. So ideally, we would specify a 32-bit memory address to jump to, but unfortunately, we don't really have that luxury, because we also need to store a 7-bit opcode, and also we need to store a destination register where we're actually going to be returning to once we've actually finished executing our function. So because of this, we cannot actually have a 32-bit immediate. Instead, we're going to have a 20-bit immediate, and we're going to have this fun format for UJ. So notice that we have an opcode, which will specify we want to do a JAL. We have a destination register, which will store in the return address, essentially, of our jump. So this is going to save PC plus 4, because this is the next instruction. For example, say I want to jump to print. I'm going to do JAL print, essentially, and then I'm going to save into RA, or RD, in this case, so JAL RA print. I'm going to save into RA the destination of the next instruction that I would execute, so then the print function knows where to return to. And finally, we have this jumbled up offset right here. So this offset is actually added to the PC and set to the PC, essentially, to do a PC relative jump. But the thing is because it's not 32 bits, we can really only jump to plus or minus 2 to the 19 locations, which, since we're doing half-word aligned instructions, is really 2 to the 18 32-bit instructions that we can jump to. As a reminder, there's two different pseudo instructions that JAL has. The first one is just the jump, which is just a J, and this is a pseudo instruction which the assembler will translate into, say I have J and then print. The assembler will translate this into JAL x0 print. So essentially it's going to be saying, I just want to jump there. I don't want to worry about jumping and linking back the return of where that function should return to. There's also a pseudo instruction JAL and then print. And this will default RD to RA, which is the return address, which is the standard register to use to specify where you should jump back to once your function is completed. And finally, you might notice this instruction is the instruction offset or immediate is very jumbled up, and this is very similar to why branch instructions are jumbled up, and that's mainly just to reduce the hardware costs. The next jump instruction I want to cover is JALer. So JALer is actually an I-type format instruction. It's not a UJ format instruction, which means it shares the same exact traits as an I-type. So we have an opcode, we have RD func3, RS1, and a 12-bit offset. And it's written just like an I-type. We have the return destination register, we have a source register, and we have an immediate right here. But in this case, we're going to call it an offset because it's a jump instruction. So it's an offset based off of whatever this value is right here. So what JALer does is it writes to RD PC plus 4, which is essentially the return address. It also sets the PC equal to the source register plus the offset. So this uses the exact same immediate as the arithmetic and load operations of I-types, which means that there is no multiplication by 2 bytes, so remember that that is not the case with this. So JALer also has some pseudo instructions as well that were covered earlier in this class. I just want to remind you of them again. So we have ret, which is equal to JRRA, which in reality is equal to JALer x0 RA x0. So basically, if you do not specify the destination register and the immediate, it's going to default those to 0. And something to note is you cannot specify one and not the other. It's either you don't specify either, or you specify both. As in, you don't specify the destination register and the offset, or you specify both the destination register and the offset. There's also another pseudo instruction, which is JALer. So you can think about it like JR is jump register. So I only want to jump to a register. I don't want to worry about jumping and going back. JALer is jump and link register, which means I want to jump to a register, and I also want to link back the return address of where I should have gone to after this function I'm jumping to is completed. So that's what JALer is. If I specify JALer and then a register which I want to jump to, it's going to actually translate this into JALer RA x1 0. So basically, it's going to put in the traditional register which will be used to figure out what the return address is. It's going to store whatever the next instruction would be into that register. And it's going to use a 0 offset because typically you won't really be using an offset in JALer. Though there might be a case where you might want to use this offset. For example, since JALer is an absolute addressed function in the sense, or an absolute jumping function, you might want to actually jump to some 32-bit value. you're able to actually do this, and you're actually able to make it a PC relative jump as well. So say I want to do an absolute address jump. I can use load upper immediate and load the upper 20 bits of some absolute address into some register. Then I can use this register plus the lower 12 bits of that immediate and actually jump to that correct location. Remember, there still is that sign extension, so you do need to be careful and make sure that this upper immediate is the correct upper immediate for the lower immediate that we have right there. Also, so this will be an absolute address jump, which means that we're not going to, if I move this code to some new location, that jump is not going to jump to the correct location. But we can actually solve this with add upper immediate to PC, which is PC relative. Say I know that this location is going to be constant distance away from me, but it's going to be relative, but I know that all this code is going to be moved at the same amount, which means that this offset is essentially never going to change. I can use add upper immediate to PC instead to actually fill in the upper 20 bits plus the current PC, and then I can load in the lower 12 bits when I actually do the jump, so then I can actually do a PC relative jump with Jaller. So this can be very useful as well, and Jaller is in general a very useful function that you will definitely end up using if you are writing functions in RISC-V.